Hi, my name is Michelle Cooke, and I'm presenting this talk on behalf of Jen Hatch, former lead buyer, and Hannah Elston. In today's talk, I'll share with you our ongoing investigation of the San Gorgonio Pass region of the San Andreas Fault, which is a complex transpressional bend along that system. The San Andreas Fault has complicated geometry in this transpressional bend with two potential pathways for slip and rupture. We don't yet know how slip is partitioned among the northern pathway, shown here in orange, and the southern pathway, shown in green and purple. The yellow circles on this map all show sites of geologic slip rate investigation. Recent activity on the southern pathway is well established, but debate persists on the activity of all portions of the northern pathway. Kendrick et al. Estimate zero slip in the last 100,000 years at Raywood Flats, Site 5. While at Site 6, two different studies produce conflicting interpretation of whether this portion of the Mission Creek Fault has had activity recently or not. In other areas, we might turn to GPS velocities for understanding how slip is partitioned among faults, but here the faults are too close together. The GPS can't definitively resolve activity on the two pathways. In this study, we used boundary element method forward models to simulate the long-term geologic slip rates on these faults and explore the deformation of the fault system. Using these models, Bayer et al. Investigated 6 plausible fault geometries and assessed the match of the model predicted slip rates to the geologic slip rates. The upper plot shows the correlation of model slip rates on the San Andreas Fault, and the lower panel shows the correlation for the San Jacinto Fault. Even though we did not change the geometry of the San Jacinto Fault in any of these models, slip along this fault responds to changes in fault geometry and subsequent slip rate on the San Andreas. Because these faults are soft link, we included slip rates along both faults in the assessment. While the inactive Mill Creek model performs best, Model 6 also has low mismatch. In Model 6, slip passes from the Mill Creek to the Galena Peak Fault and bypasses Raywood Flats, where Kendrick documents unfaulted landslide deposits. We can't rule out or confirm activity along the northern pathway using this comparison of slip rates. By the way, I encourage you all to watch the recorded presentation of Elston et al., where we use focal mechanism to try and delineate between these two best fitting models. What do I mean by kinematic compatibility? If the interpreted geometry of the active fault system is able to reproduce slip rates that are consistent with the geologic rates, then the two are kinematically compatible. When we plot the slip distribution along the fault through the San Gorgonio Pass from Cajon Pass to the Indio Hills, we see that neither model recovers all of the geologic slip rates. Vertical bars here indicate the geologic slip rate ranges, and the bands show the model predicted slip distribution. The slip rates at many sites match well in both models, but some match one or neither model. For example, Badger Canyon overlaps the model slip rates here for the inactive Mill Creek model, but doesn't match the model slip rates when Mill Creek, the northern strand, is active in the model. In contrast, Washington Street site here on the Banning Fault matches when the northern pathway is active in the active Mill Creek model, but doesn't overlap the model slip rates in the inactive Mill Creek model. Then there are some sites, such as the Pushwalla site, which barely touches and doesn't overlap the model slip rates in active Mill Creek and misses by quite a bit the model slip rates in the inactive Mill Creek model. This indicates that the fault geometry and the slip rates are kinematically incompatible. Here we explore how the model responds when we force the model to slip within the range of the geologic slip rates. We do this by prescribing slip at the site that fell outside the geologic ranges when the faults were freely slipping in the model. The left column are the same slip rate distributions that you saw previously. On the right are the slip distributions where all of the sites are limited to slipping within the geologic ranges. The adjusted sites are marked with vertical arrows. With these adjustments, sites such as Pushwala in the inactive Mill Creek model, not only does the slip rate match an increase to the geologic slip rate, but the slip rate also increases along the Mission Creek away from that Pushwala site. Overall, the active Mill Creek model has a greater number of sites that are adjusted, more arrows in this model, but the inactive Mill Creek model has a larger amount of adjustment. To assess how the slip rate adjustments affect the kinematic compatibility of the whole system, we investigate distortion maps. Distortion is the sum of the divergence and the vorticity, and it shows the off-fault deformation within the model. The map, with shades of purple, shows the total distortion from the freely slipping model. The presence of off-fault deformation in these models indicates that some permanent strain in this region is not taken up as fault slip, but as off-fault deformation. These red plots now show how the distortion maps change when we adjust the slip rates at the site so that they all lie within the geologic ranges of slip rate. The colors of the circles at each site indicate the degree of adjustment. Green are sites that fell within the geologic ranges and were not adjusted. Yellow sites were adjusted a little bit, and then warmer colors were adjusted by greater amounts. The gray ellipses highlight the regions where we see significant all-fault distortion, which signals significant increases in kinematic incompatibility between the fault geometry and the geologic slip rates. Interestingly, some adjusted sites do not increase off-fault deformation, while others produce large off-fault distortion. The Painted Hill site, for example, even though it was adjusted, doesn't really make any significant distortion nearby in either model. In contrast, the sites along the San Bernardino, which also have small adjustment, produce significant distortion. There seems to be more wiggle room with some sites than others, in that Painted Hills could slip a little more or less and doesn't seem to impact the system in either model. Meanwhile, other sites seem to have big impacts on the system. We need to know more about how fault slip rates respond in these areas of distortion. And in this analysis, we've adjusted all the sites at once. So to unpack this a little bit more, we want to assess the sensitivity of individual sites by changing each site independently. We did that by applying 1 millimeter per year of strike slip at each of the sites listed in the first column of this table, and then we assessed the impact of that 1 millimeter per year on all the other sites. The diagonals are all 1%, reflecting the self-impact. It is maybe not surprising that the sites that are very close to one another, such as in the Indio Hills, have a large impact on one another. But then it's interesting that the sites along the San Bernardino strand, which are much farther apart, also seem to have a high impact on one another, even though they're more distal to each other. Also, the sites in the San Gorgonio Pass seem not to impact each other, even though they're at similar distances, maybe because each of those three sites are on different fault segments. This chart tells us how the sites are impacting each other, but there's a lot of real estate in between these geologic slip rate sites. So in our next analysis, we apply that 1 millimeter per year at each site and then investigate the change in slip rate along the faults. Here's an example. We apply 1 millimeter per year at Badger Canyon, and this changes the slip to the northwest and southeast of that site. And when we overlay that on the map, we can see that the 1 millimeter per year at Badger Canyon impacts slip on the San Bernardino down past Plunge Creek, but not much further along that fault. We can integrate this impact along the fault and come up with a single impact factor, which represents the impact that 1 millimeter per year at Badger Canyon has on the fault system. We do this for each of the sites. And here we're showing, upper plot shows the impact of each site within the active Mill Creek model, and the lower plot for the inactive Mill Creek model. A couple of things jump out. First off, sites that are close together don't necessarily have the same impact. 1 millimeter per year on Pushwala has a much larger impact on the whole system than 1 millimeter per year at Three Palms, even though it's just a couple miles down the road. This means that some structural positions have much greater impact than others. We also noticed that the geometry of the system changes the relative impact of different sites. For example, Badger Canyon has a very large impact on slip when the Mill Creek system is active and less so when in the inactive Mill Creek. Not all slip rate sites are created equal. This means that if we have an error or we're off in our estimate of slip at any one of these sensitive sites, it may have a large impact on the behavior of the system. In conclusion, our analysis shows incompatibility between geologic slip rates and our interpreted fault configuration near Indio Hills and also along the San Bernardino Strand if the northern pathway of the San Andreas is active. We need better constraints in these regions. The SSIP study led by Puis has a different dip to the Garnet Hill and Banning faults, and we're currently analyzing these models. Another interesting outcome of our study is that geologic slip rates are not created equal. Some sites have greater potential to delineate between models. For example, Badger Canyon and Biskra Palms are examples of sites who are not matched in the active Mill Creek model, but are matched by the inactive Mill Creek model. In contrast, Washington Street site's slip rate is matched in the active Mill Creek, but not the inactive. And then finally, site impact factor provides an interesting way to assess the impact that errors or uncertainties of slip rates at sites could have on our understanding of strain partitioning along the whole fault system. It's interesting that structural position seems to matter quite a bit more than we expected, so that even sites within the same region have different impacts on the system. Thank you for your attention.